On December 15th, 1967, at 4:58 p.m., the Silver Bridge collapsed without warning during rush hour. 46 people died. 37 vehicles plunged into the Ohio River. The National Transportation Safety Board's investigation revealed no overload, wind, or external force caused it. Instead, a single tiny flaw in one steel component grew over 40 years into a catastrophic failure. The case highlights critical lessons in materials science, structural redundancy, and inspection practices. The bridge, opened in 1928, used innovative heat-treated high carbon steel eye bars, high strength, approximately 105 psi ultimate in parallel pairs for suspension chains instead of cables. Each link had only two eye bars sharing the load for low redundancy, lower weight, lower cost, less materials, lower cost. Pins connected them at joints like C13N near the Ohio Tower. Towers rested on rocker bearings, so losing chain continuity caused immediate progressive collapse. The innovative heat-treated carbon steel eye bars used in the Silver Bridge represented a significant advancement for the era. These were long, flat bars, approximately 2 inches by 12 inches wide, 45 to 55 feet, made from medium to high carbon steel, commonly identified as equivalent to SAE AISI 1060, around 0.60% carbon content. The steel was heat treated, quenched and tempered to achieve a high tensile strength, typically an ultimate tensile strength of about 105,000 psi, yield strength around 75,000 psi, and allowable working stress of 50,000 psi, allowing fewer parallel bars per chain link, only 2 instead of the traditional 4 or more, for cost savings and lighter design while still carrying the required loads. The innovative heat treatment eye bar chains used the 2-bar link as opposed to the multi-link of other bridges. This heat treatment produced a microstructure with higher hardness and strength but reduced ductility, elongation, and failure, often as low as 5% compared to 18% in conventional mild steels, and notably low fracture toughness, especially in thicker sections. The material exhibited brittle behavior at service temperatures, with Charpy V-notch impact energies as low as 3 to 7 joules at room temperature, and a high ductile to brittle transition temperature around 90 degrees Celsius or higher in some tests, making small cracks prone to sudden cleavage fracture under stress. This bridge, again, the Point Pleasant Bridge, used the 2-bar link system. It had no redundancies but high strength. Only 2 link bars were used. It reduced the weight and the cost, but if one bar failed and the 2-bar had to support the entire bridge, would rely only one link. These eye bars, connected with the pins, made a chain much like a bicycle chain. These chains made up the upper cord of a Warren-type stiffening truss. There were 7 panels on each side span and 12 panels on the main span. The detailed diagram of construction of joint U7 of the north truss of the Ohio side spanning, showing the joint pin, the two sets of eye bars, gusset plates attaching members of the north truss to the eye bar joint, retaining plate, and the retaining pin, which was inserted through a concentric hole in the joint pin, which was installed with two nuts on either side of the retaining pin. The makeup of the retaining pin, the retaining plates, and the use of double nuts on each end of the retaining pins were common to all eye bar joints at the time at the tops of the two towers and the connections of the eye bar chain with the chain bent posts. The rocker type towers were 313 feet tall and were designed to move with the bridge. The towers were 313 feet. Detail of expansion joint of connection of truss to chain bent post. The initiating failure, a cleavage or brittle fracture in eye bar number 330, which was the north bar north chain Ohio side span, at joint C13N, a small semicircular crack, approximately 0.1 inches deep. In the eye's inner surface, split the lower half brittly, then the upper half ductily. This let the companion eye bar number 33 slip off the pin, severing the chain. The collapse of the silver bridge originated from a small pre-existing flaw in eye bar number 330, a critical component in the north suspension chain at joint C13N. This flaw, a semi-elliptical crack approximately 0.1 inches deep, initiated at a corrosion pit on the inner surface of the eye, likely due to fretting wear at the pin interface combined with environmental exposure. The eye-bar steel was a heat-treated high-carbon grade equivalent to AI SI 1060 process to achieve high tensile strength, ultimate 105,000 psi for efficient load carrying in the innovative 2-bar per length chain design. However, this heat treatment resulted in elevated hardness and reduced ductility in thicker sections, yielding low fracture toughness at service temperatures. Consequently, the material exhibited brittle behavior once the crack reached a critical size, propagated via cleavage fracture under normal tensile stresses amplified by geometric concentrations at the eye head, and secondary effects such as joint rotations and traffic-induced vibrations. This flaw grew slowly over the bridge's 40-year life through the synergistic mechanisms of stress, corrosion, cracking, where sustained tensile stress and mild atmospheric corrosives, including moisture and possible sulfur compounds, promoted intergranular crack advancement and corrosion fatigue, in which cyclic loading from vehicles accelerated propagation along the crack front. The material's microstructure, high hardness from heat treatment, offered low fracture toughness, allowing a sudden cleavage brittle fracture once the crack reached critical size under normal service conditions. The single failure severed the non-redundant chain, triggering catastrophic progressive collapse. In 1927, when the bridge was designed, these environmentally assisted cracking phenomena were not recognized in heat-treated steels under typical rural exposure conditions, representing a key materials knowledge gap. The configuration of two bars meant that the failure of one bar in a pair transferred the full load to its companion, which then slipped off the pin, severing the chain and triggering progressive collapse due to the rocker bearing towers. Critically, the initiating crack was located deep within the assembled pin joint, completely inaccessible to visual inspection or any contemporary non-destructive testing method without disassembling a connection, an impractical and impossible task. Key design and materials mistakes. Minimal structural redundancy. Stress corrosion, stress fatigue were not recognized. Flaw, pin location. The National Bridge Inspection Standards stemmed from this bridge collapse disaster. Long-term changes to the field of engineering or mandatory adoption of redundancy, integration of fracture mechanics principles into bridge design, and a shift towards proactive science-based inspection protocols. Recognition that long-term environmental material interactions must be addressed in design predictions. The replacement Memorial Bridge opened in 1969, incorporated redundant cable suspension for greater safety. This collapse drove the Federal Highway Safety Act of 1968. Key changes were made due to this collapse in this engineering catastrophe.